Okay, so today we are going to talk about free fall. First though, before you start the video, make sure you turn in your kinematics worksheet to your substitute teacher, and also make sure you pick up the free fall worksheet in the front of the classroom because it is your homework and it is due next class. So let's get started. So, any object that is being acted upon only by the force of gravity is said to be in a state of free fall. Freely falling objects do not encounter air resistance, or you can think of air it as a type of friction, and it's friction caused by the air. Now, in real life, there is air resistance. So when we talk about free fall in this class, we are under the assumption that literally gravity is the only thing acting on it. So we're ignoring the effects of air resistance when we talk about free fall. So real quick, let's ask ourselves a question. Which object of these two would hit the ground first? A feather or a bowling ball? Yes, a feather. Why is that? Take a second and think about it. Hopefully you said air resistance, and this is true. The air resistance acts on the feather, causing it to fall more slowly than the bowling ball. So if we could eliminate air resistance and have these two objects be in perfect free fall, which would fall faster? Most of you are probably thinking right now it's still the bowling ball. And if I asked you why, you would probably say because it's heavier, which might have been what you said to begin with when I asked you which of the two fell further. Well, we're going to watch a video where we are going to drop these two objects without any air resistance. And to do that, we are going to use the great guys at BBC who teamed up with NASA to do this experiment for us. So let's watch the video. The video that we're about to watch was pulled off of YouTube. Credit goes to BBC, and I have included the citation, which includes the link to give them the credit they are due. Let's watch the video.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exactly. Exact. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant.
So, as you can see, two objects in the absence of air resistance will fall at the same rate regardless of mass. So see that right here. In the absence of air resistance, all objects fall at the same constant acceleration regardless of mass. So earlier when we were talking about the bowling ball and the feather, and we said that even with air resistance, the feathers fell more slowly than the bowling ball. The answer was not that the bowling ball fell faster because it was heavier. Even with air resistance, that is the incorrect answer. The reason the feather fell more slowly than bowling ball was because of air resistance. And if we remove air resistance, we can truly see that mass does not matter, that the two objects would fall at the same rate regardless of mass if we did not have air resistance. So near Earth's surface, the acceleration due to gravity is negative 9.8 meters per second squared. It's 9.8 meters per second squared down, and we give it the sign negative because that's how we signify the direction of downward. So gravity is always acting downward. There is nowhere on Earth where gravity does not act downward. When we say downward, we mean towards the Earth's center. This value can be found in the constants section on your equation sheet, so you do not have to memorize this number. All right, let's do a few check questions. If you drop a ball off a cliff, what is its acceleration? Well, we just said that all objects encounter the same acceleration no matter what. So the answer here is 9.8 meters per second squared down. If you throw a ball upward, what is its acceleration? This is a common one people misunderstand. They think it's on the way up, so it's not accelerating down. Well, we just said on the previous slide, the acceleration on any object at any time is always 9.8 meters per second squared downward. So that's the answer here for number 2 as well. Let's think about that for a second. When the ball is on its way upward, it actually slows down as it gets to the top. Well, as it's going up, the velocity is upward and it's slowing down, so the acceleration must have the opposite sign, so it makes sense that the acceleration would be downward. At the top of its motion, when the velocity is momentarily zero, what is the ball's acceleration? So when you throw something up in the air, it does reach a maximum height at some point. And at that point, the velocity is actually zero for an instant. Even at that point, the acceleration is still negative 9.8 meters per second squared. So don't think that just because something stopped, it can't be accelerating. It's just its instantaneous velocity of zero. It was slowing down. It's in between slowing down and speeding up. So it does have to hit a point of zero somewhere in there. So for all 3 of these check questions, the answer is 9.8 meters per second squared downward. There are a few characteristics of free fall that we need to talk about. So once objects are in free fall, they always have a downward acceleration. We've kind of been talking about that the last few slides. So at any point, if an object is in free fall, we are going to say that the acceleration is negative 9.8 meters per second squared. Even if the velocity is positive, negative, momentarily zero, it doesn't matter what the velocity is. If an object is in free fall, we say that it has a downward acceleration of negative 9.8 meters per second squared. At the top of its motion, when the velocity is momentarily zero, again, the acceleration is still 9.8 meters per second squared downward. It says 9.81 here. That's another number often used, but we're just going to use 9.8. At the maximum height, so any object that's thrown in the air, when it's at its maximum height, the velocity is zero. This is only true if it's in one dimension. So if we throw something straight up, we're not in two dimensions yet. We'll talk about that more in the next unit. So for this unit, at the maximum height, because we're in one dimension, the velocity at that maximum height is zero, and you can see that signified in this picture right here. When distance up equals distance down. So if you throw something up and it comes back to the starting point. So if this problem was not off of a cliff, if we threw the ball up and it came back down and it was going to end at the same spot it started, you could see that the distance up will be the same as the distance down. When that is true, the time up is also the time down. So however long it takes something to go up a certain distance, it's going to take it the same amount of time to go down that distance. Now let's bring this back to what we talked about earlier in this unit. Let's take free fall and graph that motion. So what would the position versus time graph and velocity versus time graphs of an object free falling from rest look like? Now we're going to assume we're just dropping something. We're not throwing it in the air. So if we take an object and we drop it off a cliff, what would the position time graph look like? Well, in order for us to drop it, it has to be above the ground. So our graph is going to start somewhere up here. And it's going to move downward, so the slope should be negative. And because it's going downward and accelerating downward, it's going to be speeding up. So the slope of the graph should be getting more steep. So your graph looks like this. Notice the slope is very shallow or gentle right here, so it's starting slowly, and it's getting more steeper as time goes on. But the whole time it has a negative slope, signifying that it's going downward. Now, let's talk about what the velocity time graph would look like for this motion. It's going downward the whole time, so notice we are going to draw this below the x-axis, and it's speeding up, so we should be getting further away from zero. And it's a constant acceleration, so it's a constant slope, so it's a straight line like this. Notice it starts at a velocity of zero, and the slope of this line should be the acceleration, which is negative 9.8 meters per second squared, which remember I said you can think of that as meters per second per second. Alright, so the last thing we're going to do today is work practice problems based on these ideas. We've already talked about the three kinematics equations, but those were just for objects moving really in the x dimension. Now we're going to go to the y dimension and talk about when things are in the air, gravity is acting on them, and they're in free fall. When we approach free fall problems, there's three things we need to do. First, we will set the acceleration of gravity. So the acceleration for any problem, if it's in free fall, is 9.8 meters per second squared down, and mathematically we'll call that negative 9.8 meters per second squared. When we do these problems, we're going to use one or a combination of the three kinematics equations. So know that those are going to be the tools that you're going to use to solve these problems. And in all our free fall problems that we do mathematically, we are going to assume there is no air resistance. The only time we will account for air resistance is conceptually, and you'll see that in short answer and multiple choice questions. So mathematically, we will always assume there's no air resistance. I try to always put this on the problem, but sometimes I don't remember. Alright, so let's get started on the problems. Okay, so this first problem says a student drops their homework down a wishing well. Now I put this note from rest so that you can see anytime we say drop, that implies that its initial velocity was at rest. So when I drop something, I'm not giving it an initial velocity by throwing it upward or throwing it downward into the well. So the next part of the problem says, after 2.4 seconds, it hits the water at the bottom. How deep is the well? So on these problems, the best way to start is to write what you know. So we definitely know the initial velocity is 0. And that's implied by the statement from rest, or it drops their homework. We know the time that the homework is in the air is 2.4 seconds. Okay. We are looking for how deep the well is. Now, a lot of people's misconception would be it hits the water at the bottom means it's going to have a final velocity of 0. This is not true. So when the object actually hits the water, it does not have a velocity of 0. It's only after it hits the water and the water exerts a force on the homework that it stops the homework. And then it's no longer in free fall. So the homework actually hits the water with a velocity. So we actually don't know the final velocity here. The last piece of information we know is that the acceleration is negative 9.8. Oop, that does not look like an 8. Let me fix that. 9.8 meters per second squared. Okay? So these are the pieces of information we know, and we need to find delta x using this. So if you look on your equation sheet and you find an equation that has these 4 variables and these 4 variables only, notice we do not have v final. So there's only one equation we have that does not have v final, if you remember from going over our kinematics equations. So that equation is delta x equals v initial times t. Oop, I'm going to make that clearer. Put in parentheses from the get-go. V initial times t plus 1/2 a t squared. Okay, so now we're going to plug into this equation. Delta x equals, our initial velocity is 0. Our time is 2.4 seconds plus 1/2 negative 9.8 meters per second squared times 2.4 seconds squared. Okay, so if you notice 0 times 2.4 seconds, that goes away. So delta x equals, and if we put this in our calculator, 1/2 times 9.8 times 2.4 squared, we get negative 28.224 meters. Now, let's think about why we got a negative here. What does that mean? That means that the homework actually displaced 28.224 meters down. Okay? If you look, though, the problem asked, how deep is the well? So if we know that it took 2.4 seconds to get to the bottom of the well, and in that time it will have displaced 28.224 meters down, then the height of the well is 28.22 meters. That's your answer. All right, let's go to the next problem. Okay, now we have a student stands on the edge of a 45-meter high cliff. So I'm going to go ahead and draw my cliff. And here's my little guy. And he's standing on the top of the cliff. They throw their physics homework straight up into the air at 12 meters per second. Notice they throw it up. Okay, so their homework goes up. There it is. So that means that the initial velocity, V initial, is a positive 12 meters per second. It's positive because it's up. Okay, so how long does it take to come back down to the same height as the student? So let's think about the things we know here. We are not given information about time, so we don't know that. The object is in free fall, so we do know that the acceleration is negative 9.8 meters per second squared. The V final, we do not know. But we're looking for how long does it take, so that's definitely what we're looking for. Whoops. What we are looking for in this problem is time. Okay, and the last thing is we know that if it comes back down to the same height as the student, let's think about what that means for displacement. If it comes back to where it started, what will its displacement have been at that point? The answer is 0. Okay, think about that for a second. So if it comes back exactly where it started, if we take the final position minus the initial position, that's 0. It hasn't displaced any. So that was our key piece of information here. So if we look again, find an equation that has these 4 variables and these 4 variables only, it's the same equation that we used in the last problem. So delta x equals v initial times t plus 1/2 a t squared. So let's plug in. Our delta x is 0. V initial is 12 meters per second. Our time is what we're looking for. Plus 1/2 negative 9.8 meters per second squared times time squared. Okay, now a lot of people get confused at this point, but the math really isn't that hard from here. What we're going to do is first we're going to get one of these things to the other side. So I'm going to subtract this 12 meters per second times t to the other side, and I get negative 12 meters per second times t equals, I'm going to go ahead and multiply the 1/2 times the negative 9.8 meters per second squared, and that gives me negative 4.9 meters per second squared times t squared. Okay? Whoop. Now, one thing I'm going to do is I'm going to try to get rid of, there's 1 t over here and 2 t's over there. So I can either think of it as canceling 1 out, or I can divide both sides by t. What happens here is this t cancels out, and one of these t's goes away. So you're left with negative 12 meters per second equals negative 4.9 meters per second squared times t. Now it's a basic algebraic equation. To solve for t, I divide both sides by negative 4.9 meters per second squared. Okay, both of those cancel out. And so both of these negatives cancel, so that it becomes positive. And if I put this in my calculator, 12 divided by 4.9, I get positive 2.449 seconds equals t. Now, remember we talked about this time has to be positive. So if I got a negative number, I would have known that I did something wrong. But that comes out, and that is an S. I know a lot of my S's and stuff have looked like 5. So 2.449 seconds. Okay, let's go to the next one. So this one's actually the same problem. It's just asking a different question about the scenario. So it says, if it falls all the way to the bottom of the cliff, how fast is it traveling when it hits the ground? So we've got our same cliff, and it's 45 meters high, so I'll draw that right here. Okay. They throw their physics homework straight up. So we have that person again, and they take their homework and throw it straight up at 12 meters per second. But this time, it's going to go all the way to the bottom. Okay, so let's think about the stuff we know in this one. The initial velocity is still the same. It's positive 12 meters per second because it's thrown upward. The acceleration is still the acceleration of gravity because it's in free fall. So negative 9.8 meters per second squared. We don't know the time. we do want to know how fast it will be traveling when it hits the ground. That'll be v final. That's what we're trying to find. Now, we want to know that velocity when it hits the bottom. So what is the either time it takes to hit the bottom or displacement from its original position when it hits the bottom? And we can figure out its displacement. So its displacement from the time it started till it'll hit the ground will be 45 meters down. So we'll call that negative 45 meters. Because it will have gone down negative 45 meters at the time we want to know the final velocity. So if we take these 4 variables and find an equation, it's actually a different one this time. It's going to be v final squared. Sorry, I haven't been good about putting my vectors on top. V initial squared plus 2a delta x. Okay, so plugging in v final squared equals v initial squared, so positive 12 meters per second squared plus 2 times negative 9.8 meters per second squared, whoop, times negative 45 meters. And it's so crucial that you get that negative on that 45 because it does displace downward to get to the bottom of the cliff. So now let's do a little algebra. We still have v final squared equals 12 squared. It will be a positive 144 units squared 2, so meters squared over second squared. Okay, plus if we put everything over here to the right, 2 times a negative 9.8 times a negative 45. Those negatives cancel, so we're left with a positive value of 882 meters squared per second squared, because we have meters times meters per second squared. Now, if you notice, these two numbers have the same units, so we can just add them together. So v final squared equals 882 plus 144 is 1,026 meters squared per second squared. To get v final and get rid of that square, we need a square root. So we'll square root both sides. So v final equals, now if you remember from your math class, the square root of something is always plus or minus that value. 32.03 meters per second. Now the square root gives us 2 values. So now we have to actually think logically about which one is correct in this scenario. So if it's hitting the bottom of the ground at the bottom of the cliff, is it going to be going downward or upward? Well, it's obviously going to be moving downward. So the answer is 32.03 meters per second downward. Now, one thing I didn't explain that I want to make sure you get is these units right here. When we square this as well, that's how we got the meters per second. So the square root of meter squared is meter, and the square root of second squared is second, so that's where we're left with a meters per second. Okay, let's move on to number 3. A football is kicked straight up in the air at 15 meters per second. So we've got our little guy. There's a little foot. There's our football. I can't really draw this good on my iPad. But he's going to kick it straight up at 15 meters per second. And somebody's going to criticize me for not giving him arms, so I'll do that. How high does it go? Okay, I'm giving you a hint. In order to solve this problem, you need to think, what is the velocity at the top? Well, if you remember from our notes earlier in this lesson, we said that the velocity at the top, so we're going to call that v final, is 0. So this is at the top. Okay? Now we already know v initial is positive 15 meters per second it's in free fall, so the acceleration is negative 9.8 meters per second squared. And we want to know how high does it go. So in order to find that, we will find the delta x. So this will be delta x at the point when the final velocity is 0, which we know happens at the top of its flight. So let's look again for an equation that fits these 4 variables, and it's the one we used on the last problem. So v final squared equals v initial squared plus 2a delta x. So plugging in our values, v final is 0, so 0 squared is just 0, equals positive 15 meters per second squared plus 2 times negative 9.8 meters per second squared, and the displacement is what we're looking for. So I'm going to go ahead and do a little algebra to clean it up. 0 equals 15 squared is 225 meters squared per second squared plus 2 times a negative 9.8 gives us negative 19.6 meters per second squared times delta x. Okay, now I need to isolate that delta x, so I'm going to move the 225 to the other side. So to do that, I will subtract it, so it'll be negative 225 meters squared per second squared equals negative 19.6 meters per second squared times delta x. And in order to isolate delta x, I'm going to divide both sides by 19.6 meters per second squared. Make sure I divide the negative. So those cancel. So delta x equals 225 divided by 19.6 gives me, the negatives cancel, so it's positive, a positive 11.48. And if we look at our units, the second squareds cancel, one of the meters cancels, and we're left with a meter. That makes sense for displacement. So it doesn't ask what the displacement is. It just has how high does the football go. So we can just write 11.48 meters for our answer. Or if you see, I rounded my answer to sig fig, so 11 meters. All right, now for part B, what is the total hang time? Every year I have people not understanding what this actually means. Hang time means just the total time the ball hung in the air or the ball was in the air. So this actually isn't just the time it takes to get to 11.48 meters, because that would only be half of its total flight. So we kind of need to relook at this problem. So the initial velocity is still a positive 15 meters per second. It's still going to be in free fall, so the acceleration is negative 9.8 meters per second squared. We want the total hang time, so we're going to be looking for time, but we need the time that correlates to a certain final velocity or a certain displacement. Well, we don't know what its speed is going to be when it comes back and hits the ground again, but just like that problem we did earlier, we know that when it gets back to the ground, the displacement will be 0. So if we can find the time it takes to get to a displacement of 0, which will be the time it takes to get back down to the ground, that'll give us our time. So for these variables, we're going to use the equation delta x equals v initial times t plus 1/2 a t squared. Okay. Delta x is 0. V initial is a positive 15 meters per second. We're looking for time plus 1/2 times negative 9.8, these 8s, meters per second squared times t squared. Now, if you recognize, we've actually done something very similar to this algebraically. We did a problem where we had these similar values and we were solving for time. So if you remember, we first moved the 15 to the other side, and we got negative 15 meters per second times t equals 1/2 of 9.8 is negative 4.9 meters per second squared times t squared. We divided both sides by t in order to eliminate one of them. So that t cancels, and then we have a t left over. So we have negative 15 meters per second equals negative 4.9 meters per second squared times t. In order to isolate t, I'm going to divide both sides by negative 4.9 meters per second squared. Those go away. So my time is 15 divided by 4.9, which is, the negatives cancel, give us positive, which again makes sense for time, so 3.06 seconds. And I rounded my answer to sig figs, so that's why I put 3.1 at the bottom here. Alright, so for this last practice problem, we have a ball is thrown vertically downward from the top of a 250-meter building. Its initial velocity was 4 meters per second. So I've drawn the picture already on the left. So we have someone on the top of the building. The building is 250 meters tall, and they throw the object downward at 4 meters per second. So if we think about the first values that we already know the initial velocity is going to be negative 4 meters per second. The reason it's negative is because it was thrown downward initially, so we have to give it that negative value. It's in free fall once it's released, so our acceleration is going to be negative 9.8 meters per second squared. Okay. We are looking for how long before it hits the ground. So our delta x is going to be negative 250 meters when it hits the ground. And so we are looking for the time it takes to do that. So if we look at these four variables, the equation that we're going to get is delta x equals v initial t plus 1/2 a t squared. Plugging in, I will say negative 250 meters equals negative 4 meters per second times t plus 1/2 times negative 9.8 meters per second squared times t squared. Now, if you look at this problem right now, we have a t squared value, a t value, and a constant value. So this is actually quadratic. I know I can hear the cringes and the moans already, and I'm not even there. So, if you want to use the quadratic formula to solve for time here, you can. If you are good at using your calculator and graph the function and find where it crosses the x-axis, you can do that to solve for t. But for those of you that don't like using the quadratic and don't feel comfortable doing that, something like that on an assessment or test, I'm going to show you a different way to solve this problem. So once we get to this point, realize in order to do this equation, we would have to use the quadratic. We can just approach it from a different angle. So remember, we're looking for how long it takes to hit the ground. And the first time we were doing that, we were going at it saying the displacement would be negative 250 meters when we hit the ground. But what if we could first find what the final velocity is at negative 250 meters displacement? Then once we have the final velocity, then go back and find time. So it will take us 2 steps, but we won't have to do as hard of algebra. So let's try it this way. We are going to say, what is VF? when our VI is negative 4 meters per second, our A is still negative 9.8 meters per second squared, and our displacement is negative 250 meters. So we are finding the V final when it hits the ground. So if you look at these four variables, we would use this equation. V final squared equals V initial squared plus 2A delta X. So V final squared equals negative 4 meters per second squared plus 2 times negative 9.8 meters per second squared times negative 250 meters. If we multiply each of these terms together, 4 squared is 16. The negative goes away because it's squared. So we get 16 meters squared per second squared plus 2 times 9.8 times 250. The negatives cancel because there's two of them. So plus 4,900 meters squared per second squared. We add those together and we get 4,916 meters squared per second squared. We will square root both sides in order to get VF. So square root of 4,916. We get the final velocity is plus or minus 70.11 meters per second. Okay, so obviously when it hits the ground, it's going to be the negative value. So I'm going to circle that. We know it's the negative of that. So now we are going to say, okay, I want to solve for time in this situation. So now that I know that V final is negative 70.11 meters per second when it hits the ground, I can just find the amount of time it takes to get to that speed. So I've got all values but time. So I really have any of the equations to work with. I obviously don't want to use the one up here that we used earlier because that one had to be a quadratic. So I'm going to use this one. V final equals V initial plus A times time. The V final was negative 70.11 meters per second equals, V initial is negative 4 meters per second plus negative 9.8 meters per second squared times t. So I'm going to move the 4 over and I'll say negative 70.11 plus 4 gives me negative 66.11 meters per second equals negative 9.8 meters per second squared times t. To get t by itself, I will divide by 9.8 meters per second squared on both sides. So those cancel, and t comes out to 6.75 seconds. So you can see that I was able to do this problem. It took 2 steps, but I was able to do it without using the quadratic equation. So for part B on this problem, we need to find out how long it will take to reach a velocity of 30 meters per second down. So it starts at 4 meters per second, and we want to know how long is it going to take. Somewhere down here, it will be going 30 meters per second, and we want to find out how long that takes. So the information we know V initial is negative 4 meters per second. V final is going to be negative 30 meters per second. We know the acceleration is negative 9.8 meters per second squared because it's in free fall, and we are looking for the time. So this one, the equation is going to be V final equals V initial plus A times T. V final is negative 30 meters per second. V initial, negative 4 meters per second plus negative 9.8 meters per second squared times T. So, first thing I'm going to do is add this 4 over. So, plus 4 meters per second. So that gives me negative 26 meters per second equals negative 9.8 meters per second squared times T. So then I will divide negative 9.8 meters per second squared on both sides. And I will be left with T equals, the negatives cancel out. So 26 divided by 9.8, we get 2.65. And then the meters cancel, one of the seconds, and seconds is on the bottom of the bottom, which is actually the top. So that gives us 2.65 seconds for part B. So we are not going to work this problem on this video. We will work it next time we are in class. So you are done with your lesson for today. You may now use the rest of class time for your homework.